In this video, I'm going to go over the main careabouts when adding a Wi-Fi connectivity to the IoT edge node. Among the edge nodes, there are various types of devices which present different sets of requirements and use cases, from small sensors and building automation accessories with minimal bandwidth requirements to audio or video streaming devices such as TVs, speakers, and security cameras. From gaming consoles with strict latency needs to printers or any device supporting OTA updates which prefer high throughputs. Selecting the right connectivity interface requires understanding the desired use case for the product and considering the different wireless options. The main factors to consider are the required bandwidth, range, power, security, reliability, interoperability, and ease of integration. In the following slides, we will cover in high level the concerns for each of these factors and will check whether Wi-Fi is a match. Connecting to the internet over Wi-Fi is simple, as it can be achieved using the existing infrastructure. Most houses and offices already have Wi-Fi coverage through 802.11 routers, which would easily support another connection. The Wi-Fi range is heavily influenced by the environment, like walls and other interferers, and the operational frequency band, but the typical tens of meters range will enable direct connection to an existing indoor router. While other wireless technologies require the use of extenders or a mesh network, similar solutions are available in a Wi-Fi network, but are less common and probably will not be needed for connecting the new device. The required bandwidth is a major consideration when choosing the wireless technology. An IoT sensor or accessory typically requires very low bandwidth, below 10 kilobits per second, and is idle most of the time. A smart grid, including smart meters, EV chargers, etc., only require a few kilobits per minute, a very low data rate, while a compressed video stream may require a couple of megabits per second. All of these technologies support a periodic log dump or over-the-air update, which is efficient and user-friendly. Wi-Fi can handle all of the above as the RF rates range from 1 megabits per second to gigabits per second, keeping in mind that the actual real-time application bandwidth may be different than these values due to protocols, overheads, and product design and depending on interferences over the air. TI family of Wi-Fi devices are targeting the IoT use cases with devices supporting application throughputs from 13 to 100 megabits per second. The Wi-Fi Protected Access Security defines the authentication, integrity, and confidentiality within the local area network, i.e. security over the air between the edge node and the local 802.11 access point. Texas Instruments Wi-Fi devices are compliant with the latest WPA 3.0 specification. In addition, the IoT-oriented devices provide a full set of security enablers for the edge nodes, such as secure sockets which provide peer-to-peer protection, secure data storage and IP protection, cloning protection, and provisions for security during production. Wi-Fi transmit and receive power is measured in tens to hundreds of milliamps, which is higher than alternative wireless technologies that may be used by an IoT edge node. However, the legacy 802.11 PowerSafe protocol with newer enhancements, such as the Wi-Fi 6 target wake time, or TWT, enable an idle edge node to be kept in a low power mode, waking up occasionally to receive access point beacon. This saves power by turning off the receivers for brief periods of time, only waking up the receivers when the access point indicates it has traffic for them. This mode enables the device to always be connected with an average consumption of tens to hundreds of microamps. An intermittent connection can be used to reduce this number if the edge node doesn't need to wake up on network events. The TI Wi-Fi devices support the standard protocols and offer non-standard options such as the long sleep interval to extend the sleep time and enable even battery-based always connected applications. Wi-Fi enables smarter energy management by emphasizing real-time awareness of energy consumption. The Wi-Fi original 2.4 GHz band used to be a bottleneck. The limited number of Wi-Fi 20 MHz channels together with other wireless technologies operating at the same range made it very congested with impact on the overall performance. The 802.11a spec added more sparse channels in the 5 GHz band. The latest standard of Wi-Fi 6E adds a third band in the relatively unexploited 6 GHz, with up to 100 new 20 MHz channels compared to the original 11 channels in the 2.4 GHz. There are growing design challenges for Wi-Fi connectivity as there is an increase in IoT devices and thus a higher need to operate in all types of environments, especially high-density ones. Some challenges with designing Wi-Fi in high-density environments include ensuring consistent RF performance and reliable connection, ease of design for various architectures, and coexistence with other wireless technologies. Fortunately, today's Wi-Fi can handle a variety of home and industrial IoT applications, and provides reliable, consistent, and efficient connectivity in the IoT market. Wi-Fi gives us secure, reliable connection when it counts. Because the standard keeps evolving to satisfy new requirements and ever-growing demand for bandwidth and availability, more and more products and configurations are being brought to the market, which raises an interoperability challenge for the edge node that must be able to connect and operate with all the available products. The Wi-Fi Alliance certification program tries to make sure that all devices are compliant to the specification and thus are interoperable. However, some aspects of the specification and certification process are ambiguous, such that one solution may not work with another, or at least won't enable an efficient operation. Texas Instruments' long experience with Wi-Fi has already resulted with many integrated interoperability fixes to many such issues. Our interoperability lab includes more than 230 access points, with new ones being added frequently to make sure our devices are compliant with most of the existing access points. Wi-Fi is natively mapped to TCP/IP, and with most of the Wi-Fi adapters come a driver that integrates to a TCP/IP stack. The Wi-Fi access points are typically integrated within an IP router. This makes the internet access straightforward without a need for a dedicated protocol gateway. The Wi-Fi edge node can easily access the cloud through management services such as DNS, ICMP, and SNMP, as well as communication protocols such as HTTP, MQTT, and many others. Texas Instruments' Wi-Fi devices can be integrated to the Linux network stack, thus enabling all of the Linux IP applications, or support multiple operating systems and network stacks. In addition, TI Wi-Fi devices also support the integration with certain cloud vendor SDKs, such as the AWS and Azure. The recently announced Matter framework is also supported. There are additional factors that need to be considered before choosing the most appropriate connectivity device, and there are more decisions to make after the Wi-Fi is selected. The next decision would be to choose the product that works for your application. Regardless of the final decision, Texas Instruments can help. At TI, we offer a large portfolio of Wi-Fi devices supporting different software and hardware architectures and optimizing various use cases. In addition, we offer solutions as both ICs and fully certified modules. We hope that you can now effectively choose the right device for your system. If not, TI engineers are here to help you choose. For more information, please visit ti.com/Wi-Fi.